Let's discuss the derivative. As encountered in a calculus course, it's primarily a computational tool. We learn some rules, and then we focus on the applications of the derivative. In this course, we'll instead focus on proving all of those rules, detailing the relationship between continuity, differentiability, and ultimately integrability, and exploring pathological examples that run counter to our intuition. We do get a small taste of formality in Calculus 1 with the limit definition of the derivative. And so the graphical motivation for this definition is likely familiar. We want to define the derivative at some point c to be the slope of the tangent line to the curve. And so we formalize that by choosing some nearby x value, connecting a secant line between our point at c and our point at x, calculating the slope of the secant line with this difference quotient, and then taking the limit as x approaches c. So let's write out this definition. Let f from I to r be a function defined on some interval I. Given c and I, the derivative of f at c is defined by f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c, provided this limit exists. In this case, we say that f is differentiable at c. If f prime at c exists for all points c and I, we say that f is differentiable on I. And with this definition, it's meaningful to talk about the derivative at the endpoint of our interval, because then the limit just becomes a one-sided limit. Let's consider two basic examples. Consider the power function x to the n, where n is a natural, and let c be an arbitrary point in the reals. Let's note this identity that x to the n minus c to the n could be factored as x minus c times this sum, and then we can calculate f prime at c as the limit as x approaches c of x to the n minus c to the n over x minus c. We can replace that numerator with our factorization and cancel since we know x is not equal to c. And then plugging in x equals c to each of the remaining terms, we have n copies of c to the n minus 1, or nc to the n minus 1. Let's consider the function absolute value of x. This is a continuous function, and yet it won't be differentiable at the origin. For x values greater than 0, the difference quotient, absolute value of x minus absolute value of 0 over x minus 0, simplifies to 1. And when x is less than 0, the difference quotient simplifies to negative 1. So the limit as x approaches 0 of this difference quotient doesn't exist, so the function is not differentiable. So this demonstrates that continuity doesn't guarantee differentiability at a single point. But we'll even be able to push this much further, and in a few videos we'll look at an example of a function that's continuous everywhere and nowhere differentiable. The reverse implication does hold. Let f from I to r be differentiable at a point c and I, then f is continuous at c. Let's begin our proof by noting the existence of two limits. The limit as x approaches c of the difference quotient exists and equals f prime of c, because f is differentiable, and the limit as x approaches c of x minus c exists and equals 0. And we can express f of x minus f of c as the product of the difference quotient times x minus c. Therefore, by the algebraic limit theorem, the limit of f of x minus f of c exists, and the limit as x approaches c of f of x minus f of c is equal to the limit of these products, which is f prime of c times 0, which is 0. So limit as x approaches c of f of x equals f of c. Thus f is continuous at c. Let's prove some more basic derivative rules. Let's list the sum rule, constant multiple rule, product rule, and power rule in a single theorem we'll call the algebraic differentiability theorem. Let f and g be functions defined on an interval I, and assume both are differentiable at some point c and I. Then f plus g prime at c is f prime at c plus g prime at c. Kf prime at c equals k f prime of c for all k in the reals. Fg prime at c is f prime at c g of c plus f of c g prime at c. And f over g prime at c is g of c f prime of c minus f of c g prime of c over g of c squared, provided that g of c is non-zero. The proof of 1 and 2 are fairly straightforward, so let's just sketch out the proof of 3 and 4. To prove 3, let's examine the difference quotient for fg. We can rewrite it like this, expanding out fg of x to f of x g of x, same with the fg of c, and then both add and subtract f of x g of c. so that we could factor an f of x from the first two terms and a g of c from the next two. Now, by our previous result that differentiability implies continuity, the limit as x approaches c of f of x is f of c. So, taking the limit of both sides and applying the algebraic limit theorem for functional limits, we get the full result. We can prove part 4 in much the same way. Let's write out this difference quotient for our quotient function, and then we can simplify this algebraically, getting a common denominator in the numerator and then combining that with the existing denominator of x minus c. And then we'll do the same trick of adding and subtracting the same thing to find difference quotients hidden within this expression. So we'll add and subtract f of c g of c to the numerator, and we'll factor a g of c from the first two terms and an f of c from the second two. We split this into two fractions, and we can cancel out the g of c in the first, since we've taken it to be non-zero. Taking the limit of both sides and using the continuity of f and g, we can write that f over g prime at c is 1 over g of c f prime of c minus f of c over g of c squared g prime of c, which is equivalent to the quotient rule expression. And the one more important Calc 1 rule that you'll recall deals with compositions of functions, the chain rule. Let f from a to r and g from b to r be such that f of a is a subset of b, so that the composition g of f is defined. If f is differentiable at c in a, and g is differentiable at f of c in b, then g composed with f is differentiable at c, with the derivative of g composed with f at c equaling g prime at f of c times f prime at c. We can write out the difference quotient for this composition expression, and a natural first intuition would be to multiply and divide by f of x minus f of c, so that we could split it up into two fractions like this, so that we could take the limit as x approaches c and recognize the first one as g prime at f of c and the second one as f prime of c. We're going to be a little bit more careful than this because this makes the unjustified assumption that f of x minus f of c is non-zero. Since g is differentiable at f of c, we could write out the definition of the derivative expression for g prime of f of c like this. Let's call that difference quotient d of y. With this declaration, the limit as y approaches f of c of d of y is g prime of f of c. But we encounter the subtlety of d of y not being defined when y equals f of c. So let's actually define d of y piecewise to be this difference quotient if y is not f of c, and to just be g prime of y if y is f of c. And this makes d continuous at f of c. Let's rewrite the equation d of y equals this difference quotient without a fraction, multiplying both sides by y minus f of c. And now because d of y has that piecewise definition, this holds for all y and b, even y equal to f of c. So for any x in a not equal to c, we can substitute y equals f of x and divide by x minus c. Now taking the limit as x approaches c and applying the algebraic limit theorem proves the chain rule. Another derivative rule encountered in Calc 1 and often just used without proof is for finding local optima. The claim there is that a maximum or minimum can only occur on a differentiable function where the derivative is 0. Let's state this as a theorem. The interior extremum theorem says let f be differentiable on an open interval a to b. If f attains a maximum value or a minimum value at some point c in the open interval a to b, then f prime of c equals 0. A maximum value here just being defined as f of c being greater than or equal to f of x for all x in the open interval a to b. For the proof, let's consider two input sequences, xn and yn, which both converge to c, and xn is less than c is less than yn for all n. Since f of c is a maximum, f of xn minus f of c and f of yn minus f of c are both less than or equal to 0 for all n. And we can recognize f prime of c as the limit of two distinct difference quotient sequences. Firstly, we can look at the sequence f of yn minus f of c over yn minus c, and note that it's less than or equal to 0 for each n, because that numerator is less than or equal to 0 and that denominator is greater than or equal to 0. Since f prime of c is the limit of this sequence, f prime of c is less than or equal to 0. And on the other hand, if we consider the difference quotient f of xn minus f of c over xn minus c, that's always greater than or equal to 0. The limit of the sequence of difference quotients of that form will also be f prime of c, and so f prime of c is greater than or equal to 0. Since f prime of c is both greater than or equal to 0 and less than or equal to 0, f prime of c equals 0. This is the fact that justifies the technique in applied optimization problems where we set the derivative equal to 0 to solve for critical numbers. Let's look at one more theorem. Darboux's theorem states that if f is differentiable on a closed interval a to b, and alpha is strictly between f prime of a and f prime of b, either way around, then there exists a point c in the open interval a to b, where f prime of c equals alpha. This is essentially saying that the intermediate value property holds for derivatives. Even though derivatives aren't necessarily continuous on closed intervals, they can't have any jump discontinuities. You might object to this claim thinking of the example we considered earlier, the absolute value of x. If we differentiate this everywhere it's differentiable, it appears that the graph does have a jump discontinuity. However, it was not differentiable on any closed interval containing 0. For the proof, it'd be nice to deal with a more specific case, so let's define g of x to be f of x minus alpha x, and we can note that this g is differentiable on ab, with g prime of x equal to f prime of x minus alpha. But recasting our hypothesis in terms of g, we get that 0 is strictly between g prime of a and g prime of b, and we just need to show that there exists a c in the interval a to b such that g prime of c equals 0. So the picture for this simplified case with the function g would look something like this. Our function has a negative derivative at a and maybe a positive derivative at b, and it's differentiable, which we know kind of means smooth, and so it has to have some point in between a and b where the derivative is 0, where the curve is flat. To prove this, we'll be able to use our prior result, which gives the conclusion that the derivative is 0, but the hypothesis for that result was that our function attained either a max or a min value at some point in the interval. Since g is differentiable on the closed interval a to b, it's continuous on that closed interval, and thus by the extreme value theorem, it has a maximum and a minimum value. But in order to apply that previous result, we need either a max or a min in the open interval a to b. So we need to rule out the possibility that these are both on the endpoints. We know that g prime of a is less than 0, and g prime of b is greater than 0. Or it could technically be the other way around, but that'll be a very similar case. So let's assume that this is the case. Then visually, we can see that neither of the endpoints could be a min. Let's make that argument. By the definition of the limit, we can choose x naught in the interval close enough to a, such that g of x naught minus g of a over x naught minus a is less than 0, because the derivative is less than 0. Since x is greater than a, g of x naught minus g of a is less than 0, or in other words, g of x naught is less than g of a. So g doesn't have a minimum at a, and then a similar argument will show that g does not have a minimum at b. But it has to have a minimum somewhere in this interval, so we conclude that there exists some c in the open interval a to b, such that g has a minimum at c. And then by the interior extremum theorem, g prime of c equals 0. Picking our heads back up and looking at the start of our argument, f prime of c equals alpha, proving Darboux's theorem. In the next video, we'll discuss the mean value theorem.